So in a given problem, it is given that the induction motor is operating from a balanced 3-phase load and which is taking a current of 10 amperes at 0.8 power factor lagging, and if we connect a star connected capacitor bank at the motor terminals, then what is the percentage reduction in the losses will be? Because as we know that the induction machine will always takes reactive power from outside. So if there is no capacitor bank there, it will take the reactive power, that means indirectly in the form of reactive current, which will be taken from the outside. So as a result, the losses of the motor may increase. For example, if you connect a capacitor bank which will be supplying the reactive power required for the induction machine, so it will not take that reactive power from the outside, so that the current which is drawing from the outside, which is a combination of the active and this one, what we call useful and non-useful power, or we can say active power and reactive power. So if you connect the capacitor, what will happen? It will not take the reactive power from the outside, because the capacitor will itself will supply the reactive power. So as a result, it will not take much current when compared to the current when there is no capacitor. So as a result, what I can say was the current, especially the reactive current which is drawn by the induction machine, will come down because of the capacitor bank connection at the terminals of a induction machine. So I'll see how much is the reduction in the losses, because once you find out the change in current or the reduction in the current, you can find out the reduction in the losses. So first, if you see, the motor is taking a current of 10 amperes at an angle of at a power factor of 0.8 power factor lag. So that means this is minus cos inverse of 0.8. So this I can write this as 10 at an angle of minus 36.87. That is also equal to 10 into cos of 36.87 minus j sin of 36.87. So this is equal to 10 into 0.8 minus j into 0.6. So this is 8 minus j 6 amperes. So that means it is drawing 8 amps of current corresponding to active power, and this is a current 6 amps corresponding to the reactive power. So if I connect a capacitor bank, I'll see how much reactive power or how much reactive power that will be given by the capacitors. So he has given the capacitor value. So you find out the per phase capacitance. Per phase capacitance is given as 25 microfarad, and find out per phase capacitive reactance, that is Xc, that is equal to 1 by 2 pi f into C per phase. So this is equal to 1 by 2 pi 50 into this is 25 microfarad. So if you simplify this, you will get 127.32 ohms. This is the reactance corresponding to the capacitors. Now the current, the capacitive current is equal to V per phase by Xc. So V per phase is 400 by root 3 by 127.32. So this is equal to 1.81 amperes. So this capacitors is supplying 1.81 amperes. So that means the net reactive current drawn from supply is equal to, earlier it is drawing 6, now 1.81 is supplying from its terminal itself. So this is equal to 4.186 amperes. So now it was reduced from 6 amps to 4.186. Now the total current drawn from the supply is equal to the active current, that is 8 minus J 4.186 amperes. So the current, if I see in the form of magnitude, this is square root of 8 square plus 4.186 whole square. So this is 9.02 amperes. But he is asking the losses. So we know that the losses are proportional to the current square. So the percentage reduction in loss is equal to, so if I consider this as I2 and the first one as I1, so the change is I1 minus I2, because it is losses I am talking about. I1 square minus I2 square by I1 square into 100. So I1 you know, I2 you know. If you substitute, you will get 18.47 percentage. So from the given options, the answer is 18. So which is option D.